Welcome to today's ArXiv CS Digest for March 11, 2026. We received 643 new computer science papers today across 49 subfields. Let's dive into the top picks. Up next, our first paper out of 5, Shadow in the Cache, Unveiling and Mitigating Privacy Risks of Cache Cache in LLM Inference by Jifan Luo and Zhang Qin from State Key Laboratory of Blockchain and Data Security, Zhejiang University. Let's break down its key contributions. This paper provides the first comprehensive analysis of privacy vulnerabilities in the Cache cache, demonstrating that sensitive user inputs can be reconstructed. This foundational work establishes the critical problem of Cache cache privacy leakage. 3 distinct attack vectors are designed and implemented: a direct inversion attack, a potent collision attack, and a semantic-based injection attack. These methods practically demonstrate the severity and feasibility of Cache cache privacy leakage. Cache Cloak is proposed as a novel, lightweight, and efficient defense mechanism to mitigate the identified privacy risks. It offers a practical and robust solution for securing LLM inference against various attacks. Cache Cloak utilizes a reversible matrix-based obfuscation scheme, combined with operator fusion, to secure the Cache cache. This specific technique ensures robust security with virtually no degradation in model accuracy. Up next, our second paper out of 5, IH Challenge, a training dataset to improve instruction hierarchy on frontier LLMs by Chuang Guo and Kai Xiao from OpenAI. Let's break down its key contributions. This paper introduces IH Challenge, a novel reinforcement learning training dataset specifically designed to improve instruction hierarchy robustness in LLMs. It addresses challenges like instruction following failures and nuanced conflicts. The methodology involves fine-tuning a frontier LLM, GPT-5 Mini, on the IH Challenge dataset using reinforcement learning. This process is enhanced by online adversarial example generation to further improve instruction hierarchy robustness. Up next, our third paper out of 5, Empirical Pack-Based Bounds for Markov Chains by Vahe Karagulian and Pierre Alquier from ESSEC Business School, Sergi. Let's break down its key contributions. The paper introduces a novel pack-based bound specifically designed for data generated by Markov chains. This extends generalization theory beyond independent observations, addressing temporal dependencies in data. This new pack-based bound incorporates a crucial parameter called the pseudospectral gap, gamma ps. This quantity characterizes the dependence structure within the Markov chain, making the bound more tailored to sequential data. A significant innovation is the development of an empirical method to estimate the pseudospectral gap, gamma ps, particularly for finite state spaces. This eliminates the need for prior knowledge of unknown data-generating constants. By empirically bounding the pseudospectral gap, the paper achieves the first fully empirical pack-based bound for Markov chains. This makes the generalization guarantees practical and applicable without strong assumptions on data properties. Up next, our fourth paper out of 5, Simulation in the Reasoning, a conceptual framework for empirically grounded AI in autonomous transportation by Wuping Xin from Caliper Corporation. Let's break down its key contributions. Introduces the Simulation in the Reasoning, framework, embedding domain-specific simulators directly into the LLM reasoning loop. This transforms LLM reasoning from narrative plausibility into an empirically grounded, falsifiable workflow. Proposes the Model Context Protocol, MCP, as the mechanism for LLMs to invoke and interact with external traffic simulators. MCP enables the LLM to execute intermediate reasoning steps as simulation experiments. Establishes a novel hypothesis simulate-analyze workflow within the LLM reasoning process. LLMs formulate strategies, invoke simulations via MCP, evaluate results, and refine hypotheses through iterative verification and aggregation. Up next, our fifth paper out of 5, a TreeGuard, defeating indirect prompt injection in LLM agents via causal attribution of tool invocations by Yu He and Zhang Qin from Zhejiang University. Let's break down its key contributions. This new paradigm secures LLM agents by asking why a tool call is produced, distinguishing user-intended calls from those driven by untrusted observations. It shifts defense from input semantics to action causality. A tree guard implements causal attribution using runtime parallel counterfactual tests. For each proposed tool call, it re-executes the agent under a control-attenuated view to verify its necessity. This mechanism is crucial for preventing attribution confounding during counterfactual tests. It ensures consistent agent behavior by guiding the shadow execution, enabling accurate causal analysis of tool invocations. This component suppresses diverse control channels from external observations while preserving task-relevant information. It strategically filters untrusted content to isolate the causal impact on tool calls. To robustly handle LLM stochasticity, a tree guard employs a fuzzy survival criterion. This criterion allows for slight variations in tool calls during counterfactual re-execution, making the defense more practical and resilient.